New pictures captured by the James Webb Space Telescope have stunned researchers. Rather than reinforcing our perspective on the universe, these photos reveal a disturbing reality. Our current understanding is insufficient to grasp the vastness of the universe in its early stages. Where the theory of the universe's early phase reaches its limits, we are led to consider new hypotheses about its origins. The question arises: how was the universe formed in detail? And why does this new discovery challenge even the most experienced space experts? To understand more about the Big Bang and its ever-evolving nuances, we must reassess the concept of the event itself. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Rather, space itself began expanding approximately 13.8 billion years ago, along with matter and time. In cosmology, a singularity describes a point where gravity is so intense that the curvature of spacetime becomes infinite. Today, billions of years after the universe's beginning, we see that our cosmic home is part of a vast and interconnected system. For scientists, this represents a fundamental aspect of the universe's existence: its continuous expansion. The universe is not expanding into pre-existing space. Instead, space itself is continuously growing. According to standard theories, the first stars began shining between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Ages. This was when the first luminous celestial objects clustered together to form mature galaxies. However, how quickly these galaxies formed remains an ongoing mystery. A major clue emerged through the first images captured by the James Webb Space Telescope in July 2022. Experts reported that the telescope had detected several galaxies, some of which existed around 300 million years after the universe's formation. Compared to galaxies that formed billions of years later, these early galaxies were significantly smaller and less massive, aligning with existing scientific models. The density of matter in the young universe was believed to be too low to form galaxies as large as those observed today. This changed with the discovery of 6 unexpectedly bright redshifted objects by the James Webb Telescope, which triggered one of the most significant cosmic crises of recent times. Although these newly discovered galaxies are similar in age to previously recorded ones, they are nearly as massive as our own Milky Way galaxy. This has created a fascinating mystery in Big Bang cosmology. Upon analyzing a series of images taken by the near-infrared camera, researchers identified these light sources. Using redshift analysis, scientists confirmed that the light from these objects took more than 1 billion years to reach Earth. This means these structures had already existed between 570 and 700 million years after the Big Bang. Remarkably, these galaxies were so massive that they defied conventional cosmological assumptions. Instead of detecting typical dwarf galaxies, researchers found structures nearly as large as the Milky Way, despite having formed very early in the universe's history. If we continue to examine the data collected by the James Webb Space Telescope, we find that this gravitationally bound collection of stars had already reached more than 10 billion times the mass of the Sun at that time, with one galaxy possibly reaching an unfathomable 10 billion solar masses. However, even if this possibility is accepted, the mystery remains unresolved. There would have been far more mass in the early universe than previously expected, presenting a major challenge to existing cosmological models. The observed galaxies defy nearly all traditional theories. Even if just one of these galaxies is confirmed to be genuine, it would force us to reconsider our previous assumptions. The density of matter in the early universe would have to be several times greater than currently believed. Another equally puzzling explanation suggests that these galaxies formed in a way that remains completely unknown to us. These discoveries and the discussions they provoke will likely lead to a reevaluation of the Big Bang theory. Many astrophysicists with alternative viewpoints are expressing their skepticism, often publishing their perspectives in scientific journals. However, those who question established theories are sometimes dismissed as controversial or radical. Even scientists who still support the Big Bang theory continually face unanswered questions. These include fundamental issues such as: why and how did the universe emerge from nothing? Could something truly arise from nothing? Or was there a triggering event? Or was it all a coincidence? Stephen Hawking proposed that the concept of time as we understand it began with the Big Bang. Therefore, the process could not have been triggered by something external. A related question concerns the uniformity of radiation and matter distribution across the universe. No matter which direction or distance we observe, we find similar densities and distributions of galaxies, nebulae, and radiation. Current scientists explain this phenomenon through the theory of cosmic inflation. However, some experts extend this idea further with the hypothesis of chaotic inflation. According to this concept, expansion has only stopped in certain regions like bubbles, while continuing indefinitely elsewhere. This suggests that multiple universes could form within these bubbles, each with its own unique physical laws. From this perspective, an intriguing question arises. What if our universe is not the totality of existence? More specifically, what if another universe existed before ours? If so, the Big Bang might be part of a larger cycle. In this view, our universe is part of a greater, more complex structure, where a perpetual cycle of collapse and rebirth takes place. However, this is not the only alternative theory in cosmology. In 1955, for example, an article published by NASA's Hotshot suggested that there may never have been a Big Bang at all, proposing that the universe has existed for an infinite period. Under this model, the expansion of the universe would be an illusion, with the continuous formation of matter giving the appearance of constant growth. Another fascinating and controversial hypothesis comes from the fields of quantum physics and string theory. Some experiments suggest that our universe, and everything in it, might be a projection or a higher dimensional simulation. While this may sound like science fiction, it is linked to the Kardashev scale, which measures a civilization's technological advancement based on its ability to harness energy. If a Type 3 civilization were capable of fully utilizing the energy of an entire universe, it might have created a perfect simulation. However, determining the validity of such a theory is an incredibly complex challenge. Exploring the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the fundamental nature of our reality, challenging established theories and prompting researchers to rethink core aspects of cosmology. At the heart of this inquiry lies the theory of the universe's origin, a cornerstone of modern cosmology. According to this theory, about 13.8 billion years ago, the universe emerged from an extremely dense and hot state, expanding rapidly and giving rise to the space-time and matter we observe today. Simply a blast inside earlier space, it additionally consolidated the earliest start of space itself, the possibility of a peculiarity where gravitational forces are so serious that the curve of space-time becomes endless. This supports how we might understand this early huge epoch. Yet the discovery of early systems by the James Webb Telescope challenges assumptions about how rapidly structure shaped in the universe's earliest stages. These universes, identified within a couple hundred million years of the Big Bang, appear surprisingly evolved and massive when contrasted with current cosmological models. One of the key questions raised by these revelations is the concept of cosmic inflation. According to the common theory, inflation happened within parts of a second after the Big Bang, making the universe expand drastically. This rapid development would explain the consistency of the vast microwave background radiation observed across the universe today. However, recent discoveries suggest complexities in the early universe's development that might require changes to inflationary models. The development of galaxies like those seen by the Webb Telescope forces cosmologists to rethink the conditions and cycles that govern the universe's early history. These universes, now gigantic and huge so soon after the Big Bang, propose a density of matter that surpasses past estimates. The mystery deepens when considering how such large structures could form and evolve in such a short time. Furthermore, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up most of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain unclear. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang view. Some hypotheses suggest that our universe is simply one of many in a vast multiverse, each with its own unique physical laws and constants. These ideas, arising from advances in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One theory gaining traction is eternal inflation, where universes continuously emerge from a larger, expanding space. This theory suggests that our universe could be just one bubble among countless others, each with its own set of physical properties. The challenge lies in finding observable evidence to support such speculative ideas, as they stretch the boundaries of observational validation. Another provocative theory posits that our universe exists within a simulated reality, akin to a computer-generated recreation. This idea draws parallels to advances in artificial intelligence and computational science, where simulations can reflect complex systems with remarkable fidelity. If true, our perception of reality as a distinct physical universe could be entirely altered, raising significant philosophical and scientific questions about the nature of existence. Moreover, advances in observational cosmology continue to reveal the vastness and complexity of the universe. Telescopes like the James Webb Space Telescope, with its exceptional sensitivity and resolution, promise to uncover even more mysteries of the universe. Future observations may shed light on the earliest moments of the universe, offering clues about its ultimate fate and the fundamental principles governing its evolution. Beyond observational cosmology, particle physicists are investigating the fundamental particles and forces that shape the universe. The mission to unify gravity with the other three major forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. Models like quantum gravity and string theory offer potential frameworks for understanding these fundamental connections at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the concept of time itself remains a subject of intense debate. Quantum theories suggest that time might be evolving or even subtle at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape how we interpret the universe's origins and evolution. Additionally, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's examination of exoplanet environments, may provide evidence of biosignatures indicative of life beyond Earth. Furthermore, scientific pursuits and philosophical reflections on the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration continue to drive investigation and conversation across disciplines. As the James Webb Space Telescope continues to return critical images and data, it opens new avenues for exploring the universe's structure and origins. One particularly fascinating aspect of this mission is its ability to shed more light on the role of supermassive black holes in galaxy formation. These enigmatic objects, found at the centers of many galaxies, are believed to play a crucial role in the development of cosmic structures. By studying the earliest galaxies captured by Webb, scientists hope to understand whether these black holes formed shortly after the Big Bang and what impact they may have had on the evolution of galaxies in the early universe. In addition to uncovering the mysteries of galaxy formation, the data from Webb also provides crucial insights into the conditions that led to the creation of stars and other celestial bodies. One of the key areas of focus is understanding the process of star formation in the first few 100 million years after the Big Bang. These early stars are believed to have been significantly different from those we observe today. They likely formed from primordial gas and were much more massive, burning through their fuel at a much faster rate. The light emitted by these early stars is an important component for understanding how the universe began to evolve from a dark, featureless state into the energetic, complex universe we see today. The discovery of early galaxies that challenge existing models also raises questions about the role of dark energy in shaping the universe. Dark energy is a mysterious force that is believed to drive the accelerated expansion of the universe. Some cosmologists suggest that the rapid expansion observed in the early universe might have been driven by dark energy, a theory that could explain some of the unexpected features of the early galaxies seen by Webb. Investigating this force and how it interacts with the universe's structure is an essential next step in unraveling the mysteries of cosmology. With each new discovery, we are forced to question our assumptions about the universe, pushing the boundaries of scientific knowledge. As researchers continue to analyze the data from the James Webb Space Telescope, they are uncovering additional insights that could revolutionize our understanding of the early universe. One such revelation is the potential identification of the first galaxies to form after the Big Bang. These galaxies may not only provide a window into the universe's infancy but could also help scientists understand the complex processes that led to the formation of the first stars and elements. Understanding how these early structures evolved will offer insights into the initial conditions that led to the universe's present state, providing answers to long-standing questions about the universe's fundamental makeup. Furthermore, Webb's advanced capabilities enable scientists to study the atmospheres of exoplanets with unprecedented detail. This opens up the possibility of detecting potential signs of life on distant worlds. By analyzing the chemical composition of exoplanetary atmospheres, researchers may be able to identify biosignatures, such as oxygen or methane, that could indicate biological activity. This search for extraterrestrial life is one of the most exciting frontiers in modern science, as it may ultimately answer one of humanity's most profound questions. Are we alone in the universe? As Webb's discoveries continue to unfold, it is clear that the future of cosmology and astronomy is entering an exciting new era of exploration and understanding.